Welcome everyone to the next Gen 4 International Forum webinar presentation. Doing the introduction today is Dr. Patricia Pavier. Patricia is the chair of the Gen 4 International Forum Education and Training Working Group. She's also the National Technical Director of the Molten Salt Reactor Program for the Department of Energy in the United States within the Office of Nuclear Energy. Patricia.
Thank you very much, Bertha. Good morning, good evening, good afternoon, everyone. It's a pleasure to have Dr. Amanda Lines and Dr. Samuel Bryan with us today from the Pacific Northwest National Laboratory. Amanda is a chief scientist with experience in the design and deployment of online monitoring and sensor technology. She graduated from Washington State University with a PhD in analytical chemistry after earning an undergrad degrees in chemistry and chemical engineering from Purdue University. Her work primarily focuses on the development of optical sensors for highly harsh environments, just as those common to nuclear materials processing, as well as the application of chemical data science tools to enable advanced automated data outputs. Dr. Sam Bryan is a laboratory fellow at PNNL in nuclear chemistry and engineering. He joined PNNL in 1990 and has over 35 years experience in optical spectroscopy, electrochemistry, and separation science. Dr. Bryan's research interests involve the design and development of spectroscopic and spectro-electrochemical sensors for the measurement of actinides, lanthanides, fission products, transition metal complexes in aqueous and molten salt media. He also serves as an adjunct faculty member in the Department of Chemistry at Washington State University. So without any delay, I'm going to give you the floor, Amanda and Sam. Thank you very much for volunteering to give this webinar. Thank you.
All right, well, thank you so much, Patricia, for the invite to give a talk here. Sam and I are both excited to go through a lot of the work that we've been doing in the development of online monitoring technology. But before we really dive into the technical meat of the talk, we want to go through some background slides just to make sure we're all on the same page with terminology and really how these tools work. So one of the first things to note here is that when we say online or inline monitoring or variants thereof, what we're talking about is getting sensors directly onto or into a chemical process so that we can see in situ and real time what exactly is going on in that process. This type of process insider information is extremely valuable and useful in a lot of ways. Many people, when they think online monitoring, their first thought is to go to operating systems at commercial scale so that they can run those processes better, faster, safer, and more cost effectively. But online monitoring has a lot of other applications as well. That includes gaining unparalleled insight into fundamentals of the chemistry of your process, allowing engineers and operators to more efficiently develop new chemical processes, and supporting engineers, operators, scientists as they go through the scale-up of a process, from lab to bench to pilot to deployed scale systems. Really, online monitoring is an incredibly valuable tool through the entire life cycle of chemical process development to deployment. And so we might ask a question then, how is this valuable to nuclear energy, or really if we think next generation reactors? And if we go right to what most people think of when they're thinking nuclear energy, which is reactor operation, when we think about Gen 4 reactors, there's at least one very good example where online monitoring could be incredibly valuable, and that is molten salt reactors. Getting sensors into or onto a molten salt reactor would not only allow operators to, let's say, look at and better understand your uranium 3-to-4 ratio, but it could potentially support other things such as material control and accounting or even safeguarding of material. So plenty of value there. But we like to argue that if we're thinking about the future of nuclear energy, we need to be thinking about the entire fuel cycle, and online monitoring can have benefits throughout. That includes supporting fuel production to power these new reactors, fuel recycle so that we can use our resources more responsibly, and of course, waste disposition once we're ready to take some of those final materials into a deep geologic repository and process them into a form that's appropriate for that. So there's a lot of applications for online monitoring through this whole cycle, and Sam and I are going to be giving you some examples of this through our talk. But before we get to that, it's worthwhile to note that there are a lot of different online monitoring tools and sensors out there. Really, the sensor tool that you utilize is dependent on what type of information you want to get out of the process. So thermocouple for temperature or so on, right? Our team utilizes whatever sensor we need to go after the information we're most interested in, but really one of our favorite tools out there is optical spectroscopy. And that's really because optical spectroscopy is unique in its ability to give us very detailed chemical composition information. This approach is all about getting light into your chemical process, looking at how light interacts with that material, and then gleaning that chemical composition data information from that very simplistic, we'll say, interaction. In this case, optical spectroscopy is something that will let us ask and answer questions such as, in this chemical process, is plutonium present? How much plutonium is there? What oxidation state is it in? What speciation is it exhibiting? Really, what is it doing in that process? And is it behaving the way we want and need it to for that process to run smoothly? So optical spectroscopy is very powerful for getting that type of information, but it does have a number of other benefits as well. It's also usually a very mature technology. That means that we can go and get a lot of our components for our systems commercial off the shelf. It tends to be fairly simplistic to integrate into a chemical process, and we'll talk more about that later. But probably the most important thing for us when we're designing online monitoring systems is the versatility of optical spectroscopy. And it's versatile in a lot of ways. The first way to think of versatility is that we can take optical spectroscopy into a whole range of different system matrices to characterize the chemical composition of those. So we can look at solids, liquids, gases, even molten salt. We can also take optical spectroscopy into a wide range of system scales, everything from commercial scale, where you're talking hundreds of gallons an hour, all the way down to micro scale, where you're talking microliters per minute. So a lot of flexibility. But perhaps the most important aspect of versatility of optical spectroscopy is our ability to go after a large number of chemical analytes that are of interest to the fuel cycle. So that's the entire fuel cycle. And the reason we can go after so many different targets is that there are a lot of different forms or flavors of optical spectroscopy that we can utilize. So, for example, two of our favorite tend to be Raman spectroscopy and UV-vis near-IR absorption. Now, Raman spectroscopy is a form of vibrational spectroscopy. It lets us get polyatomic species, so we can use Raman to identify and quantify targets such as oxide ions, organics, that's both solvent components as well as complexants. We can look at inorganic oxygen ions, water, acid. We can even do pH of weak acid-base systems. So there's a lot of things we can go after with Raman. UV-vis near-IR, however, probes the system a little bit differently. This is a form of electronic spectroscopy, so we can see different things such as actinides and lanthanides in multiple oxidation states, as well as various metal ligand complexes. Now, Raman and UV-vis near-IR are not going to give us everything we need all the time, so there are other tools that we can and have used in the past. That includes things like FTIR, light scatter, optical density, and there are many, many more, fluorescence, and so on. All of that to say that there are a lot of different optical tools that we can bring to bear in these different chemical processes to go after the target analytes of interest. But I want to pull this string a little bit more here, this idea that we can use optical spectroscopy to go after so many analytes, and just emphasize what I think is one of the greatest strengths of optical spectroscopy, which is we can get a large number of target analytes from just one single probe or one signal technique. That means, for example, if we look at Raman, we can get one probe into a process, and we can use that one probe to identify and quantify a large number of potential targets that are in that process. And I've got just a couple here listed as examples. What this means is we can really reduce our footprint into the chemical process where we have a lot of hazards. It's a little bit difficult to get in there. And we can really start being a lot more efficient with how we go after information and how we pull stuff out of a process in terms of understanding. Now, some folks might look at this and they might question whether this is truly the greatest strength. Yes, we don't have to have 20 probes here just to go after 20 analytes, but is this really all that great when you think about a process where all of these analytes are present and all their fingerprints are going to be overlapping and your data is going to become complex? Some people might look at the title of this slide and question whether this is truly a great strength in the realm of nuclear material processing, or if this is actually a weakness since our data becomes similarly complex. Well, Sam and I are going to show you a series of examples here coming up of applications that we've done in the past, and we're going to present an argument that this really doesn't need to be a weakness of optical spectroscopy if you take the right approach to data analysis. In fact, in the example applications we have coming up, you're going to see that we'll be addressing quite a few of the challenges that we anticipate in nuclear material processing schemes. Many of these are actually unique to nuclear materials processing, so developing online monitoring tools to overcome them is essentially the specialty of our team. But just to give you an example of some of the challenges that we deal with, we have to deal with environments that damage our sensors in a very powerful way. So think of highly corrosive or very high temperature systems. Molten salts are good examples of both of those. We also have environments with high radiation that can cause darkening of our optics or windows or other materials that we have to compensate for and be ready to adjust for. We also tend to work with processes where the process conditions can complicate analysis. So examples are very turbid processes or variable turbidity processes, systems where we have very sensitive matrix effects or confounded signals, and we are talking nuclear materials processing. So one of the biggest challenges we have to face are that we have a lot of processes where frequent calibrations or probe maintenance, or think any access to that probe, is just simply not realistic because it is in a hazard zone. So what do we do about these challenges? Our team actually goes after these challenges with two prongs of focus. We look at sensor hardening and design as one of those first prongs. So this is really focusing on our engineering of probes, material science of probe material choice, all of that to make sure that these probes can go into the harsh environments and survive for extended periods. So think molten salts as an example. So this is a big aspect of what we do, and that can overcome quite a few of these challenges that we're looking at. But the other aspect of what we do, and this is really how we start overcoming some of those complexity in data, some of those impacts to data from things like radiation damage and so on. The other aspect of what we do is make sensors smart. Really what this means is that we build advanced algorithms that can take in the highly complex data we anticipate from a real nuclear materials process and translate that into information. And when I say information, think something like a real-time readout of uranil concentration, something that an operator can immediately understand and utilize in a decision-making process. Now, before we get into the applications, I want to talk just a little bit about what this looks like in practice. And sensor hardening and design is probably a bit more straightforward, and you'll see some examples of that. But I do want to give you some background on this idea of making sensors smart. Because again, this is probably one of the key aspects of making sure that we can take optical spectroscopy, or really a lot of sensors, into a nuclear materials processing environment and get out useful, accurate, and reliable information. So it's really building that robust pathway to transform data into information. And what we do to accomplish this is chemometric modeling. I'm going to go through some graphical examples of how this works so that we can talk about what chemometric modeling does when we work or apply it to our data. But essentially, we're talking about a form of machine learning or a form of chemical data science that lets us translate complex data. So I'm going to start by going through a graphical example of what we would consider a very simplistic chemical system. What we're looking at here are the UV-Vis spectra of plutonium-4. So this is variable plutonium-4 as we vary the plutonium-4 concentration from 0 millimolar all the way up to 30 millimolar. And this is being done in 1 molar nitric acid. Now we can see that as we increase that plutonium-4 concentration, the absorbance of those bands increases. In fact, we get a really nice relationship here between the strength of the signal here and the concentration of plutonium. In this particular instance, we could actually pick our favorite wavelength and then plot the absorbance of that wavelength as a function of plutonium-4 concentration. And essentially what we've generated here is a single variate calibration curve, or a Beer's law plot. And now forever in the future, if we run into plutonium-4 under these precise conditions, so within 0 to 30 millimolar and in 1 molar nitric acid, we can use this calibration curve to quantify plutonium-4 present in solution. Now, this is beautiful data. It's very simplistic and it's very nice to work with. But unfortunately, in real nuclear materials processes, it's very rare that we see a system that is this clean and this easy to deal with. In fact, we tend to, we tend to see data that's a little bit more complex. What we're looking at here is UV-vis absorbance spectra of pretty much that same chemical system, what we would still consider a very simplistic chemical system. It's got nothing except plutonium-4 and nitric acid in here, except this time we've kind of cut the deck a little bit differently. In this case, we're holding that plutonium-4 constant now at 15 millimolar, and we're varying our nitric acid from 0.5 molar all the way up to 10 molar. And what we see here is a drastic change in that plutonium-4 fingerprint. Now, in this particular instance, it becomes very difficult to start applying that single variate tool we discussed on the previous slide here, because we'd have to start asking questions. We would have to ask, well, which wavelength do I want to use to quantify my plutonium? And if I'm choosing that wavelength, do I have to have a priori knowledge of nitric acid concentration? Am I supposed to assume that concentration? Am I supposed to titrate to get that concentration? All of these questions we're asking essentially translate to longer data processing. So you're no longer talking about something that you can do very quickly. You can no longer do it in real time or near real time. And you're also talking about adding uncertainty to your measurements. So especially if you're assuming a nitric acid concentration, you now can no longer have as great of a trust factor with your calculated plutonium-4 concentration. And that's certainly something we do not want. So instead of using that single variate calibration curve approach, what we're going to use is multivariate technology. So we're going to use the entire wavelength range, or we're going to be using the entire fingerprint of plutonium-4. So let's talk about what that looks like. We're actually going to zoom in on that primary response band of plutonium-4, and we'll blow it up over here on the side. And just to walk you through what happens as we change acid concentration, as we increase acid concentration, this primary band drops, scoots over, and then grows back in. So if we take this data and we build a chemometric model out of it, what that model is going to do is it's going to pull out principal components. And those principal components are essentially going to rate how important signal response is at every single wavelength to quantifying our target analyte of interest. And so that's a little bit of a mouthful. So let's take a look graphically again about what this looks like. And what we're looking at here are the principal components our model pulled out. In this case, our model said you really need 4 principal components in order to define all of the variability happening in this series of spectra. And it shows us these principal components as a function of our loadings. Now, a loading essentially indicates how important response is at a particular wavelength. A loading of 0 means not important, and a loading with magnitude means more important for quantification of plutonium-4. So we're looking at these loadings as a function of wavelengths, and this is the same wavelength range as we see up here. And so let's just give a quick example here. If we look at the wavelength range of 510 to 520 nanometers, we see that this is pretty flat. We probably wouldn't really rely on this too much for quantifying plutonium-4 if we were making the decision. And if we look at how our model's looking at that same region down here, it's giving it very low loading, very near to 0. So our model agrees with us. This isn't too important for quantification. However, this region of the spectrum where we have a lot of plutonium-4 signal activity, we see that our model's working very, very hard to capture that down here. Now, what's a lot of fun is that if you really take a good look at these principal components that our model pulled out, and you go and read through some fun literature from the 1960s, what you see is that these fingerprints of these principal components overlay very nicely with fingerprints of the different plutonium species. Now, this makes sense. We know why this band shape change happens as we increase acid concentration. It's because we're changing the speciation of plutonium-4. We're going from the mono to the di to the tetra to the hexanitrado species. And we see that our model is actually pulling that out. It is pulling out the chemistry of the speciation transition and using that to identify and quantify the plutonium-4 present. Now, what's even more fun from a chemist perspective here, in terms of the type of information we can pull out, is this little shoulder right here on this red band for the mononitrado species, right at about 470 nanometers. That shoulder actually overlays very nicely with where you'd expect the fully aquated species of plutonium-4 to be, so right before that mononitrado species comes in. And it's exciting that we see that at all, because our lowest concentration of nitric acid in this training set was 0.5 molar. And at that acid concentration, we had probably less than 20% plutonium-4 in the fully aquated state within that system. And despite having only that tiny, tiny fraction of plutonium-4 in the aquated position and absolutely no signal for the fully aquated plutonium-4 at every higher acid strength, our model is still able to try to capture that, pull that out. And that's really powerful. So if we take this a step further and we actually say, let's use this model for regression now, these are the results we're looking at here. We're looking at a parity plot where we're comparing what we measured the concentration to be based on our optical spectra with the chemometric models applied to what we knew that plutonium-4 concentration to be. And I want to highlight that we're looking at a parity plot where we've got two dimensions of variability. We've got both the variability of plutonium-4 concentration, so that impacts the signal strength of plutonium-4 or intensity. And we've got variability of nitric acid. So we're really changing that fingerprint of plutonium-4 quite drastically across this range. Now, what we're looking for on this parity plot is a one-to-one correlation between measured and known, and that's the black line here. And you can see that despite all of the variability, both concentration and matrix for plutonium-4, our data is lining up beautifully with that one-to-one correlation, indicating high accuracy of measurement. Now, this is powerful. So the next question is, what does this actually look like in practice? And so this is really where Sam and I are going to start diving into a bunch of example applications where we go after a lot of different challenges that we expect within nuclear material processing schemes. So that includes highly complex chemical compositions, extremely harsh environments, heavy variable processes, as well as demonstrations of real-time process control, and that's both manual and automated process control. And we'll start off with an example of manual process control supported by online monitoring. I'm going to go through a co-decon separation example, co-decon being the co-decontamination scheme where we take simulated dissolved used nuclear fuel or real dissolved nuclear fuel and run it through a series of separations to produce an aqueous product that is a mixed stream of uranium and plutonium. And so I'm going to be talking about some experiments we did several years ago on a bank of centrifugal contactors we have out at PNNL in a shielded glove box. This system was used for several very exciting separation demonstrations, again, a couple of years ago, but I do want to highlight this system has been utilized a lot more recently by NSP or Athena investments to do training of the next generation, as well as advance some S&T goals. But essentially what we did in this case is we wanted to make sure that we could control a separation process on a bank of centrifugal contactors in real time. And anytime you're talking about real-time process control, your first thought should be online monitoring. So in this case, we outfitted our bank of contactors with a series of sensors on all of our inlets as well as all of our outlets. So regardless of whatever's happening in the separation process, we could tell you everything that's going into the process and everything that's coming out of it. And for this particular demonstration, we were looking at simulated dissolved fused nuclear fuel. We did several runs, some of them a little bit more simplistic in terms of the feed, and others as complex as really simulating, dissolved fused nuclear fuel. That is to say, half the periodic table was in there. And so we weren't actually trying to quantify absolutely everything in there. We had a set of target analytes that we wanted to monitor and quantify. Those were primarily our active aids. And in order to get all of the actinides we wanted, we actually had to utilize a little bit of sensor fusion. So we had to get multiple optical sensors into a very small footprint in our sensor. And in this case, we were utilizing UV-vis spectroscopy to go after plutonium-3, 4, and 6, as well as uranium-4. We were using near-IR spectroscopy to go after neptunium-4, 5, and 6. And we were using Raman spectroscopy to go after uranyl and nitric acid. And of course, in some of our process streams for our more complex runs, we had a slew of other fission products or simulated fission products, many of which had their own fingerprints that interfered with what we're looking at here. And so in this case, we had sensors on all of our inlets, all of our outlets, 3 forms of optical spectroscopy. There was a lot of data coming out, a lot of data processing happening. Some of this data was very complex, but really just to show you how powerful online monitoring was here, I'm going to focus on just our aqueous product stream, which is actually one of our cleaner looking streams. You can see a snippet of data here. This is just the UV-vis absorbance data from one of our runs on just the aqueous product line. So keep in mind, there's also the near-IR and the Raman data here. But you can see here, there's a lot of band overlap. There's a lot of stuff happening. I think this is beautiful as somebody who enjoys optical spectroscopy, but our process operator didn't find this too useful. What he wanted was the real-time feed out of concentrations in that stream. So this is what he was looking at. This is a picture of the screen that we took while we were running. You can see the uranium-4 concentration in the background here. In the foreground, you can see a real-time calculation of the U to PU ratio, and behind this, there are a bunch of tabs for all of those other actinides in the aqueous product stream, as well as all of our other product stream, or all of our other inlets and outlets. And we replotted this just so we could show you how valuable online monitoring was for process control in this instance. And what we're looking at here is the percent composition within that aqueous product stream as a function of runtime. And for this particular demonstration, we were trying to show that we could hold a particular composition, so 70% uranium and 30% plutonium. That would be the horizontal dashed blue and red lines respectively. Now our online monitoring results are plotted here, solid blue line for uranium, solid red line for plutonium. And you can see that after a run started and hit equilibrium, we were outside of that 30-70 goal. Based on that, our operator made a process adjustment. That's the vertical black dashed line. In fact, the operator made several manual adjustments, so think turning a valve based on the online monitoring output, until you can see out here at the end, he really nailed that 30-70 ratio and held it within plus or minus or less than 1% error or variability there. So this is very powerful, but while this is really fun to look at out here, I will tell you that the operator's favorite part of this graph is actually this area in here. And that's really because he was empowered to have a lot of control here. This was an interesting run because we actually started the day here. So probably our first hot day of the spring, and our air conditioning wasn't working in our building. So we started the day here at about 18 degrees Celsius, and we ended the day out here at about 30 degrees Celsius, with our biggest deltas happening right in this region here. Now, separations are exothermic processes, so when you change the temperature that much, you're going to change how that separation progresses. The operator was actually able to see that and adjust for that in real time, as well as adjusting for pump lubricating and the other real-life factors we have in any separation process. So he was really allowed to do a lot to understand, control, and ultimately perfect this process. So that's very exciting. The other exciting thing here are the circles, squares, and triangles. Those are our grab samples. Things that we collect, send off to analytical laboratory, get results back. First thing to note is they agree nicely with our online monitoring output, indicating good accuracy of our measurement. But the other fun thing to note is the time differential. Those grab samples took, anywhere from a couple hours to a couple months to come back, whereas the online monitoring was coming out every 30 seconds. So every 30 seconds, our operator knew where his U was at, where his PU was at, and he could make choices based on that. So this is a powerful demonstration, and I think it leads nicely into our next demonstrations here, which I'll actually hand off to Sam to continue talking about.
Yes, thank you, Amanda. The transition here is I'm going to be talking about some of our past applications. Now I'm going to start with one of the applications, or several applications that related to the Hanford waste. I don't think I need to tell the audience here that Hanford area, which is located here in Washington State, is the location of the production of plutonium during World War II and also continued into the Cold War. And related to that, there is a lot of processing waste that went into buried underground tanks. This is a picture right here at the bottom. It shows the tank farm area. This is a series of tanks being under construction. And each one of these tanks is about 1 million gallons in capacity. And there's 177 of them in the Hanford site, containing various levels of fill of reprocessing waste, nuclear fuel reprocessing waste, or not reprocessing, or processing waste. And so the application for us, or the challenge for us, is, this waste is being destined to be immobilized in some shape or form. And we want to go ahead and put some sensors in line through the process at different locations to go ahead and measure the concentrations of the constituents efficiently. And and also the challenge is that this is a very chemically complex environment for us to measure in. Some of the past work, we have some past demonstrations related to this. Back in the early 2000s, we had a task to measure using Raman spectroscopy the oxy ions in the waste in a salt retrieval campaign. This was designed to go ahead and measure the salt cake that was being retrieved from a source tank that was going to be immobilized and run through a pipe to the vitrification plant. We designed a sensor that could measure 9 analytes, the oxy ions here, in a skid that was mounted out in the tank farm. It was designed for that, and it could run up to 40 gallons per minute in flow rate and measure these. In the late 2000s, we had another application where we supported the pre-treatment engineering platform, or the PEP platform, for the waste treatment plant, where we again had a Raman system where we could measure 9 analytes from grab samples that were taken from the PEP plant and sent to our laboratory. We could analyze the 9 analytes. It was these 8 up here that I've mentioned before, plus oxalate. And this was a fully QA/QC HAZCOR compliant procedure that we developed with a Raman probe. So we could measure these and have the analysis back to the PEP plant within a 24-hour period. And so this was really good. We supported that plant for about a year while they were running that design plan. In the early 2010s, we also supported a pilot scale continuous sludge leaching program where we use a Raman probe that could measure the bomite and gibbsite dissolved in the continuous sludge leaching project, where we can measure aluminum being dissolved as aluminate and hydroxide in real time. And this was a 24-hour, 24/7 application where we ran continuously for over 2.5 months in giving immediate feedback to the operators as they were doing the sludge leaching in this. And some of the applications here are summarized, and the techniques that we use are summarized in some of the publications I show here on the right-hand side. The next slide shows, I mentioned we use Raman spectroscopy. This slide really shows us, speaks to the reason why we use Raman spectroscopy for analyzing tank waste. This is a diagram of the best basis inventory of all the analytes, or the major analytes that are contained within all those 177 tanks out in the Hanford area. This is listed by constituent composition as a function of metric tons of each of the analytes. And all of if you sum up the major constituents, which are sodium salts of nitrate, hydroxide, nitrite, carbonate, aluminate, phosphate, and sulfate, those 6 or 7 constituents add up to equal 95+% of all the solid components in all of the tank waste out in the Hanford area. If you exclude water, 95% of what is in the tanks are Raman active sodium salts. And that's why we use Raman spectroscopy, because you can measure 95% of the constituents in one spectrum. In fact, this shows the Raman spectrum of those components that I just mentioned on the previous slide: nitrate, carbonate, nitrite, oxalate, chromate, sulfate, phosphate, aluminate. All of these species are Raman active, very strong signals. And just to mention, the peak height or peak area under each of the curve is generally proportional to concentration. These are pretty much separated quite well. In fact, using the chemometric analysis multivariate technique that Amanda had talked about previously is how we go ahead and measure these in very complicated mixtures. This is an actual waste demo where we took AP105, an actual waste from tank farm AP, tank number 105. This is a Raman spectrum of AP105 waste showing the big strong band right here for nitrate, the water manifold over here, that includes the hydroxide manifold. And I compare that AP105 actual waste with a simulant waste that we designed and made based on the known composition of the AP105, and also some of the single component standards that we used in our constructing our chemometric model. You can see the bond in the red spectrum here. You can see sodium nitrate, for example, it has a very strong band at the same location for the AP105 nitrate band, and so on. And so we build a chemometric model using some of these single component mixtures, binary mixtures, ternary, and very complex mixtures to build a complex training set to go ahead and then build a model. So we've taken this AP105 and we put it in one of our flow cells, or in a flow loop. This is the AP105 waste here. It's straight AP105 waste. It's not been processed in any way except to take the cesium-137 out by ion exchange so we can have it contact handled in our open phase rad hood. So we have a pump that we're pumping it through our flow cell. This is a cuvette flow cell. We have a Raman probe. This is a fiber optically coupled back to our spectrometer. We're able to shine light into our flow cell and measure the AP105. The spectra of the AP105 waste is shown here as a function of sample number, which is essentially a time axis. We have the wave number, so we can see the water manifold here, or the hydroxide manifold here. We see the nitrate band over here. So we start the process where we have water initially in the cuvette flow loop. Then we transition over to AP105 waste and measure that. Now we can go ahead and then use our chemometric models and process this spectral data and turn that into concentration data based on the model that we employed. And this shows the concentration in the y-axis versus time through the process. We start with water at the very beginning, then we transition to AP105 waste about half an hour into the process. And the top plot here shows the concentration of the high concentration analytes, showing nitrate, nitrite, hydroxide, aluminate, and carbonate. The bottom plot shows, for convenience, the lower concentration species, sulfate, phosphate, chromate, and oxalate. So we can follow the concentration in real time for 9 analytes simultaneously throughout this process. And this is actual waste which has not been conditioned any special way before analysis. And the next slide shows, Amanda mentioned that some of these solutions, since they're actual waste samples, are going to be highly turbid. And in fact, the tank waste out in the area, it has a lot of solids, a lot of sludge, a lot of oxides that will interfere with an optical technique. So we need to go ahead and really focus on how do we go ahead and get around the high turbidity, the high solids fraction solids solutions that we measure. The picture on this left-hand side shows a series of solutions. This is our simulant waste here, with 0% solids added, and then we add, in this case, it's iron oxide. We have 3 weight % solids, 7 weight %, all the way up to 10 weight % solids, very turbid solutions, and would present a problem for light scattering in an optical technique like Raman. Down below, we have a simulant sludge. In fact, the sludge was designed by some of our colleagues at Savannah River National Laboratory. And again, starting with our simulant waste with no added solids, all the way up to 10 weight %, you can see highly turbid solution. So the trick to measure in high turbid solutions is design probes that can get around some of the light scattering problems. We have several techniques that we're investigating. The top picture shows an example of one of our attenuated total reflectance probes that we're designing. This is based on an internal reflection element. This is a light guide that we shine our laser light down, reflects and bounces down the laser. It bounces down the light guide, and where the light bounces against the edge of the light guide, that interfaces with the solution on the other side of the that boundary, an evanescent wave is produced. in that evanescent wave, there's some attenuation of that. So we do measure some attenuation from the signal, and that goes off to our detector. We can then measure the Raman spectrum based on the sample that was in solution adjacent to this centinel reflection element. We also have several elements or several probes that we're designing. They have either close focus design. So this is a laser light coming through our probe, and we have an optical window that we focus the beam, laser beam, right at the interface between our probe window and the solution sample. Instead of sending the beam way out in the sample where it has scattering from some of the solids in solution, we have it right against the edge, so we have minimized the scattering from the particles in solution. Other types of probes are a Molten probe, again at close focus to the very edge or the surface of that element. These probes are commercial probes down below. In fact, this probe in the middle is designed by our small business partner, Spectro Solutions, and it was developed under a small business innovative research program in collaboration with them. Using that close focus probe that shows an example of some of our variable turbidity measurements, where we have from 0% added solids to 20% weight percent added solids. These series of spectra, the black line is 0% solids where there is no solids in solution, all the way to the bottom spectrum here is 20 weight percent solids. You can see that the signals are attenuated as we go for higher and higher weight percent solids. They're attenuated, but they do not go to zero. So we're able to get information from these spectra even at 20 weight percent solids. The bands I just want to point out, the band I want to focus on is this guy right here at 1050 wave numbers. That's the nitrate band. And if we, through pre-processing of this data, we can then see that band at 1034 wave numbers, that's the nitrate band. It still maintains very nice linearity, even at 20 weight percent solids with added nitrate. The next slide shows some of the variable weight percent solids data. This is, again, sodium nitrate at 0% added solids, 1% added solids, 5%, and up to 10% weighted solids. And we're looking at variable concentration of nitrate in each of these solutions. We're seeing very nice, well-shaped bands, so we can measure accurately the nitrate in solution. The second column shows a pre-processing step that we sometimes use, which is taking a first derivative of this curve. And what that does is really eliminate the problem of any noise, of any baseline noise. It really it transitions that to essentially zero. We get really nice, beautiful spectra all the way from 0 to 10 weight percent solids in this application. And the last slide it shows the signal strength as a function of nitrate concentration. The x-axis here is nitrate concentration. And from 0 all the way up to 10 weight percent, we have essentially the same sensitivity of scale. Again, because we can do the pre-processing step of first derivative, and also we do some normalization using that water hydroxide band to normalize our spectra. I just want to point out the slope of these lines are about 4 times 10 to the minus second for each one of these applications here, from 0 to 10 weight percent solids, meaning the sensitivity of this measurement has not been degraded by increasing to high weight percent solids. So the combination of probe design and pre-processing steps really does a really good job. The next application I want to talk about is pH measurement using Raman technique. And what I have shown here is a series of phosphoric acid speciation as a function of pH. On the left-hand side, this is phosphoric acid or triprotic form of phosphoric acid. As you increase the pH, you can remove a proton by titration, and it goes to the diprotic form. Remove another hydrogen by going to higher pH, you go to the monoprotic form, and then go to the fully deprotonated form of phosphate in this case. And so as a function of pH, you have a lot of speciation of phosphate. Turns out each one of these species is Raman active and has a characteristic Raman band. And this shows a spectrum of those of that speciation as a function of titration. This is the wave number across the x-axis here versus the intensity. And we can see that the fully protonated form of phosphoric acid has a band here. As we deprotonate, we go to the diprotic form here, the monoprotic form, and then the fully deprotonated tribasic form of phosphate. And just an overhead view of that same spectra as a function of pH here, you can see quite visually, the phosphoric acid bands, the diprotic form, the monoprotic form, and then the fully deprotonated form. And we can use this data as a training set. We know the spectra at each pH. We know the concentration. We can form a chemometric model. And when we plot that measured pH from our chemometric Raman model, and as a function of titration, we can overlay that. And I'm going to just point out we have several titration curves here at variable concentration of phosphoric acid. I'm going to focus on this red curve here, which is 1 molar phosphoric acid. And as we titrate the Raman spectrum, the Raman model is predicting the concentration or measuring the concentration of the pH. And we compare that with the light red symbols, which is the theoretical calculation for the pH in that solution. So we were spot on measuring with the theoretical pH for that solution with each one of these. And we can do this not just at very high concentration, but also in very dilute concentrations of phosphoric acid. We're spot on with the theoretical calculation. We can use this pH measurement in a demonstration for automated pH control. In this case, I'm showing a large beaker that is really our feed container, where we have a citric acid, weak acid solvent, which is used in a tall speak separation campaign. And it's a weak acid, just like phosphoric acid is weak acid. We can use that as a pH indicator as well, and we've built chemometric models for that, so we can measure pH based on the Raman spectrum of that. And right here, I'm pointing out the Raman probe in solution. And we have adjacent to that some electrochemical probes, pH probes, that we can measure the pH in a secondary form. So we have a secondary form for confirmation. And we also have some acid-based delivery tubes that we have in solution. So we have this set up controlled by a PLC controller. We're monitoring pH, and we're going to be adjusting the pH, and we're going to allow the PLC controller to go ahead and automatically control the pH by adding either acid or base through acid-based delivery tools, ports, tubes, to go ahead and maintain the pH at a set point. The next slide shows the results of one of our experiments. The blue line here is the pH that's measured by our Raman probe, and our set point is a pH of 2.8. We have the control zone plus or minus 0.1 pH units, so at 2.9 units or 2.7 pH units, that's outside the control zone. Our PLC pump, our PLC controller will actuate a pump to go ahead and either, if the pH is too high, it'll open a valve and deliver acid to drive the pH lower. If the pH is too low, then the PLC controller will open up a different pump, a valve, and pump in some base to go ahead and increase the pH. So we start here at within the control pH zone. We spike the solution with sodium hydroxide to push it outside the control zone on purpose. At this point, the PLC controller activates, and each one of these orange lines that I have indicated here is when the PLC controller actuated and injected some acid to drive the pH lower and lower and lower and lower until we get down within the control zone, and the automatic PLC controller stops delivering acid. And then it certainly it does get into the control zone and stays there through the experiment. I'm going to go ahead and show a series of experiments where we again start with the outside the control zone. The PLC controller pushes the pH by delivering acid to push it down to the set point. We add hydroxide to push it out of the control zone. PLC controller puts it back into the control zone. We add acid on purpose to put it out outside the control zone. Base is delivered to go and bring it back into the control zone. We've done this multiple times, and we recover quite nicely. I want to point out the Raman model is in the light blue lines that are shown here. That's the real-time monitoring for the Raman model with the PLC control. The pink line is electrochemical pH measurement from our auxiliary measurement, and those follow exactly on top of, just spot on, our Raman model. So our confirmation is that we're tracking pH properly, and we're also controlling the pH in an automated fashion. In this automated pH control, we also performed a mass balance during the extraction. This is, I've mentioned that the citric acid feed that we're using is used in a tall speak. The tall speak is a separation of the lanthanides from actinides process. And so we have a citric acid feed, and we're monitoring the UV vis for the metal quantification in this particular example. In the feed, in this case, it's a simulant. We have neodymium in the feed, and we want to go ahead and run the feed through a set of centrifugal contactors shown in the diagram here. So the squares with circles in them, that represent the centrifugal contactors. We have a bank of 4 that we used. We have a feed that we ran through the entrance of the centrifugal contactor and the raffinate stream coming out the other side. We have cross current in that, a solvent that was run through to extract the neodymium to form a loaded organic phase in the organic phase. And the rectangles that I have shown here in blue, those represent the locations on our centrifugal bank of contactors where we had UV vis and Raman probes to measure real time what went into the contactor in the feed, what came out in the raffinate, what went in the solvent, and what came out in the loaded organic phase. And what I have shown down here are the spectra that were taken in real time of the UV vis for the feed location, raffinate, solvent in, and the loaded organic. And as we can see at the very beginning, we start with no neodymium in the feed, but at 35 minutes into the experiment, we switched over to a feed that contained neodymium. We see immediate concentration or the bands related to neodymium increase across the UV vis spectrum until we stopped the neodymium feed at 90 minutes into the experiment, and then that band dropped back down again and continued on to its solvent. And we can see in the raffinate phase, or the raffinate position, as soon as we put the feed, the neodymium to the feed, we had the neodymium reporting out to the raffinate position, and also down in the loaded organic, we could see the neodymium bands coming in from the organic phase, from the extraction of neodymium into the organic phase. The next slide shows the results of this experiment, where at the beginning of the experiment, up to about 35 minutes into the experiment, where we had no neodymium in the feed at all, we were reading 0 concentration. This is the axis of concentration neodymium measured by our model at the different locations. We're measuring 0 concentration for the aqueous feed, aqueous raffinate, organic solvent, and organic product. But at 35 minutes into the experiment, when we added neodymium into the feed, we saw immediate increase in the concentration at that feed location. Within a few minutes of that, we saw the concentration of the neodymium in the aqueous raffinate increase, just like we saw the spectra increase in the last slide. We're interpreting that with our chemometric models, and we're seeing the neodymium coming out in the raffinate. Likewise in the organic product. Now notice here that there's a delta in time from the time we observe the neodymium going into the feed in the inlet of the contactor, and there's about a 5 to 10 minute lag before we see it coming out into the raffinate and the organic stream. That's because there's some neodymium in process. It takes a while before for the neodymium to work its way through the centrifugal contactor before it comes out to either the raffinate or the organic product. And we see that down here. So this is the plot we wanted to demonstrate mass balance. So we look at a difference between what went into the contactor and what came out of the contactor. This is the delta neodymium concentration. What we're measuring here, or what we're plotting here, is a delta of what went in, that's the feed plus solvent, minus the organic product, the concentration of neodymium in the organic product, plus what was in the raffinate. And so at the very beginning, when no neodymium was in the system at all, it's 0. But right when we start neodymium into the feed, we see a delta. I mean, there's an offset here, and that's because we have neodymium in process. So what went in, we're measuring it going in, but we're not measuring it coming out yet. When we get to the point that we're in steady state out here in the middle of the process, then what we're measuring going in is equal what is coming out, and we have a mass balance of 0. When we stop putting vanadium in the feed, we again see this deflection, and negative deflection this time because we don't have any going into the inlet, but we still see it coming out of the inlet. And then at the end, when everything is flushed out of the system, we get to mass balance again. So we are able to see, show and demonstrate mass balance through this experiment. I'm going to go ahead and transition now and talk about some of the applications in molten salt reactor programs. We support several programs, and two of which are the ARS campaign, that's the Advanced Reactor Safeguard and Security campaign under Ben Sapiti, and the other campaign is the Advanced Reactor Technology MSR campaign under Patricia Pavier. So I'll be talking about both these examples. In one case, we're looking at the uranium and the fuel salt, and this is a schematic of one of the Gen 4 type reactors where we have molten salt fuel that's circulating through the reactor. And the idea is to put a probe in to measure the concentration of uranium in the fuel salt. And also we're concerned about off gases coming in from fission products. And so we want to design probes that can measure both the salt at temperature. So we have high temperature sensors that we're designing, and also sensors that can that work in the highly corrosive solution, the molten salt solutions, and also in the gas system. The first slide here is showing the building of the library, or the chemometric library, the training set library that we need to go ahead and then measure uranium different oxidation states in some of these solutions. And this shows a picture of the uranium-3 in one of our cuvettes. This is a molten salt system at 700 degrees Celsius. This shows the photograph of the uranium-6 in solution. And we measured variable concentrations of uranium-4, 6 mixtures. We also measure variable uranium-4 in different eutectic fluoride melts. This shows some of the variable absorbance measurements that we use for our training set. And this image here shows our small-scale cuvette that we use to go ahead and measure the system that we use to measure the absorbance spectra and the Raman spectra of these salts. This shows a cutaway of our furnace that we have our cuvette within the cuvette holder shown here. We have the fiber optics, the light guide coming in and the light guide going out to the detector here. And so we have a cuvette, a quartz cuvette in this case, that's here. And so we can use UV vis for transmission. We also have ports that we can put Raman probes for light scattering and Raman measurements in this as well. So those measurements and others were used to then produce chemometric models. As shown here are several where the measured concentration from our model is on the y-axis, and the known concentration from gravimetric analysis is shown here on the x-axis. So we have models that measure for uranium-3, uranium-4, and uranium-6. And all of these, we have a fairly good root mean square error of prediction in the millimole concentration range or less. And this slide shows one of the experiments that we performed to look at the uranium-4 to uranium-6 conversion, where we start with using a chloride eutectic salt. This shows the concentration of uranium that we measure from our chemometric model as a function of time. And just to start out, we start with a clean eutectic with no metal involved. We add a uranium-4 salt in different increments in the first several hours and let it sit overnight. And then we add some more uranium-4 at the end of the experiment. And shown over on the left-hand side are the UV vis spectra as a result of those salt additions. So we start with clean salt. We have 4 additions of uranium-4. We see immediately the uranium-4 signature in the mid UV vis range. And then also we see the conversion over to the uranium-6 band over in this region here in the spectrum. And immediately when we add uranium-4, we get the signature of uranium-4. We can measure the concentration with our chemometric model, and we see the uranium-4 increase. But we also see the uranium-4 decrease over the course of time and under the conditions of this experiment. And what is it transition to? It transitions actually to uranium-6. And using our uranium-6 model, we're able to calculate and measure the concentration of uranium-6 throughout the experiment. And it grows in just concurrently with uranium-4 dropping out. When we sum up those two species, uranium-4 plus uranium-6, that gives us an inventory of the total uranium in the solution. And we get a really good mass balance throughout the experiment, especially in this middle region here. But if you notice, there's a discrepancy, especially at the transition periods where we add uranium to the system. We don't have exactly quantitative analysis of uranium, total uranium in the system here, here, and here. And we know why that is. We were able to pull up the cuvette during the experiment. And this is the cuvette, a photograph of the cuvette right after this fourth addition. So right when we're seeing this discrepancy, we see this nice clear solution, but we also see a lot of solids in our cuvette. So we're able to measure the uranium quantitatively in solution using our UV-Vis spectrometer and our UV-Vis models. But we can only measure what's in solution. If it's in the solid state, we can't measure that. When we let it sit overnight here, at the end of a 20-hour period, we pulled out the cuvette again, and at this point, all the uranium dissolved in its in solution. We see the nice yellow color of uranol 6 that we recognize the uranil ion in solution, and that's where we get quantitative, because all of that metal had all that uranium phase had dissolved, and we have it all in solution. Now we're quantitative. And when we add two more additions here, we filled up, and we're not seeing quantitative analysis here, is because we have, again, a precipitate of uranium in that sample. And this work was summarized in the Industrial Engineering Chem Research paper shown here on the left-hand side. The next slide is an application over in what we call reactor off-gas stream, and this work was supported under Patricia Pavier's campaign, and we're demonstrating in the off-gas system the measurement of the fission gas iodine being produced, and it can be evolved either as I2 or a chloride salt. It can come out as ICL. We're also looking at sensors to measure hydrogen isotopes. We're starting with hydrogen and deuterium, and we're moving toward measurement of tritium. And I just want to point out, this is a collaboration with our team, with team members at ORNL as well, and Joanna McFarland and her team at ORNL. And there's a nice publication here at the bottom that talks about some of our planning for this campaign and some of the work we've done on this campaign. So the first slide I want to show for I want to talk about the measurement of I2 with one of our gas sensors. This is I2 gas, and just to set this up, this is a gas tube filled with iodine gas. This is our Raman probe that we put up adjacent to our gas cell, and this is using 532 light excitation beam, and we were intending to measure the Raman spectrum, in which we did. But also, I'll just want to point out, this is a video. We can see that we get a really nice fluorescent spectrum, or fluorescence being generated, and it's pulsating actually, which is pretty interesting. And we saw that and we said, oh, this is really, really great. What we intended to do is measure the Raman measurement of this I2, but what we got in addition to the Raman measurement is also this very sensitive fluorescence band coming out. And what that fluorescence is due to, this is a spectrum from the literature of iodine in the gas phase of the UV-Vis spectrum of it, showing a nice vibronic progression, a lot of vibronic bands on top of this absorption band. We're illuminating at 532 nanometers excitation right on top of a lot of vibronic progressions. And so we're shining light and getting into an excited vibronic state, and we get a light emitting and nice fluorescence bands coming out into the visible spectrum. This is our fluorescent spectrum. They also have a beautiful vibronic progression. You have multiple from vibronic progression 1 all the way up to, we've measured them all the way up to 20, 25 vibronic progressions in each of our fluorescent spectra, which is really, really pretty, but it's also very useful. The next slide shows a series of variable pressure measurements. This is pressure as a function of temperature of measurement This is the fluorescence spectrum as a function of both temperature and pressure. The pressure is shown here. We're measuring this with our gas manifold line. We have a Raman probe with our gas measurement cell. We have a valve system where we can meter in iodine into the gas phase. We can measure that with a baryton probe, or baryton gauge. The picture shown on the left-hand side is very busy. It's very hard to see, so it's easier to see with the diagram here. We have our iodine capsule here, our metering valve. We have a Raman probe and our gas manifold measurement cell, baryton gauge, and this is on a high vacuum line. So we can measure easily the pressure as a function of temperature throughout this, and we have beautiful fluorescence spectra at variable temperature and pressure. We can use that data to then, and this shows it's just sort of a blown up version of the data on the last slide. This is the spectra on the last slide, and this is a blow up and a further blow up of that. But we have really nice strong fluorescence, weak fluorescence, alternating pulsating bands from the vibronic progressions. When we use that, we can measure with our probe the concentration of I2 in the gas phase compared to the known pressure. Again, nice one-to-one parity plot with both the 532 nanometer excitation. We've also used the red laser system for 671 nanometer excitation as well. Get really nice measurements with that. And this was summarized in the journal article Environmental Science Technology that was published just a couple of years ago. The next application is using measuring for ICL gas. In this case, ICL is actually infrared active. So we use a far IR technique using an FTIR system. We measure the ICL bands as a function of pressure. We measure this not just as a function of pressure, but at variable temperatures from 25 up to 75 degrees in the gas phase. And we're measuring it at pressures up to about 10 torr from low to up to about 10 torr. And this plot here shows the principal component analysis of this data that I'm showing over here on the left-hand side. The principal component analysis of that shows that essentially two PCs are needed to go ahead and actually define all of the character in both the variable temperature and variable pressure that we see in the ICL spectra. What PC 3 and 4 are shown here only to show that these show essentially noise, and they can be excluded. Any PCs higher than PC 2 could be excluded from forming a regression model. And we use these PCs to form regression models in multivariate method. So we have either a partial least squares method, shown in the top left plot. The top right plot shows a principal component regression method. And both of these have very nice 95, very tight error bars. You can see the 95% confidence interval being plotted here. They're very tight on both of these. But we can also use, as Amanda mentioned, the Beer's law or univariate method. Some of my colleagues say, this is such a beautiful data. Why not just use a single variate analysis, just peak height, for example, or peak area under the curve? Well, we can do that, and they form really nice models. But in this case, the univariate methods, while they work very nicely, this is the peak. It's just peak height versus a concentration curve, and this uses the peak area for concentration. You can tell that the models are not quite as accurate, and they have a lot larger error bands than the multivariate method. So again, this shows that multivariate method works very nicely for this kind of data. And this work was summarized in the Journal of Physical Chemistry and published a couple of years ago. The last application I want to talk about is looking at hydrogen isotopes. Again, we use Raman technique for this. This is Heather Felmy actually in the laboratory using a variable series of Raman spectrometers with variable wavelength excitation. We have Raman systems with blue, green, and red excitation sources. So the reason we use multiple wavelengths of light is to look for the technique that gives us the most sensitivity for the application of use. In this case, 405 nanometer excitation gives a lot better sensitivity for deuterium and hydrogen measurement. This is the deuterium band here at about 3,000 wave numbers, hydrogen band around 4,000 wave numbers. Very large separation between those two signals. Very nice, easy way to measure this using the Raman technique. As you go down to 532 or 671 nanometer excitation, you can tell that the scale is less sensitive as we go to longer wavelength excitation. And you can also see the ratio between the deuterium and hydrogen isotopes are much different as well. So in this case, we use the 405 nanometer excitation. The next slide shows a collection of some of the variable pressure measurements for deuterium. And again, doing the first derivative does a really good job at eliminating that baseline noise. And you see the baseline noise eliminated here. We use this data and others to go ahead and generate models for both deuterium. This is the measured deuterium pressure with our sensor versus the known deuterium. Same with hydrogen. We can use these models now to then predict concentrations in a variable deuterium hydrogen experiment. This shows an experiment where we start with our manifold line with two gases separated in two different chambers, hydrogen in one chamber, deuterium in another chamber. And we have our probe located at this chamber, measuring the deuterium concentration in real time. And then we open this valve. When we open that valve in the middle, the hydrogen deuterium start mixing, and we see a decrease in the deuterium signal with time because it's we're measuring in this chamber. The deuterium escapes over to the other chamber, and we see an increase in the hydrogen because the hydrogen from the original chamber is now flowing back into this chamber. So we see the deuterium over time, we see the hydrogen over time. These are the spectra as a function of time. We can then use our chemometric models to then predict the concentration as a function of time. And so the composition is shown here. Deuterium decreases, the hydrogen increases over the 25-minute experiment time. And at the end of the experiment, the dotted lines here are the measured values using our mass spec, which was also associated with the gas manifold line. We can measure the concentration by mass spec, and we measure exactly what we see with the mass spec. And this work was just recently, in this last month, appeared in the analytical chemistry with the reference right here. At this point, I'm going to go ahead and transfer back over to Amanda to give some concluding and summary remarks.
All right, thanks, Sam. So this slide right here is one of our final wrap-up slides, and we're talking about building bridges between fundamental and applied, but really what we're talking about here is a nod to collaboration. So all of the applications that we've shown here today are either the direct result of or directly benefited from collaborations with either universities or industry, where universities really help us, narrow in and expand our understanding of fundamentals, and industries really help us understand where the needs are, where the application space is, and where we can be impactful. So we just want to give a nod and say that collaborations are extremely important to us to really advance our technologies and probably to the nuclear fuel cycle as a whole and advanced reactors and nuclear energy in the future. And with that nod to collaborations, we'll go ahead and hit a couple of key takeaways here, which is that real-time process monitoring has a diverse and wide range of applications within the future of nuclear energy. And in particular, if we're looking at optical spectroscopy applications for that chemical composition analysis, there's a lot of beneficial needs, applications out in the future of nuclear energy. And in particular, if we combine optical spectroscopy both with advanced engineering of probes as well as advanced data analysis, we can really take these tools into some complex and some harsh environments. And overall, online monitoring is the tool that we need to ensure that nuclear energy can operate better, faster, safer, and more cost effectively in the future. And with that, we'll go ahead and thank all of our team members, our funding, and of course, everyone here for your time and attention. And we'll pass it back to Patricia for controlling any questions.
Thank you, Amanda. Thank you, Sam. Before we get to the Q&A portion, we just want to take a quick look at the upcoming webinar presentations. In August, we have a presentation scheduled on international molten salt research in support of MSR development. It'll be a panel session with several presenters listed there, and we look forward to that. In September and October, we have plans for overview and uptake of sodium fast reactor activities within the Gen 4 International Forum. And in October, an overview and update of the gas-cooled fast reactor activities within the Gen 4 International Forum. There are several questions that have come in. I think the one that I want to start with is represented by one of the comments, and that is the love of the real life applications. And I agree. I think that's the most exciting portion of this, is that you've reached into something that's very meaningful and directly applicable to people within the nuclear industry. And I can't echo enough that's exciting to see. So with that, I'm going to, let me raise you up so you guys can see the questions as well. And then we'll just work through the list. There's several here already. Some of these I think came in very early during the presentation, and as it moved along, you already addressed them. But the first one was, have you explored optical spectroscopy techniques for monitoring oxidation states of uranium and uranium fluorides?
So I'll jump in there, and Sam's here and he can add in as well. So we've used optical spectroscopy to go after oxidation state speciation for a lot of actinides, lanthanides, other fission products or corrosion products of interest. In terms of urinal fluorides, I guess we haven't played too much with the fluorides.
We haven't, although there's certainly applications in published reports in the literature that there's no trick. I mean, the trick is setting up your solution chemistry to handle fluorides, but they have been measured, variable oxidation states in measurements in UV vis in fluoride salts. So I'll just direct you to the research out there, just the published research. There is evidence of that, so we know it can be done. And we have not, in our group, gone into the fluorides just yet.
I do think we have a publication we got out in the last year or so, lead author Heather Felmy, where we actually looked at uranol nitrate in a system where we introduced HF, and we followed the fingerprint change in Raman spectroscopy with that particular addition.
Well, that was an aqueous system. I thought this was a molten salt application. Okay, so
yes.
if you're talking about molten salt, it's done in a lot of that. You can find that in the literature. We've not done molten salt fluoride, but we've done aqueous solution with fluoride. Yes, that's correct.
Yeah, and that's just an example of how you can go after that type of information.
Thank you. And then the next is an observation that reads, online in subloop doesn't give main loop info. You still need to back calculate what happens since the loop left the main loop. Even water reactors have to back calculate what the primary loop result would be, as sampling, even online, requires decay of high rad before the sensors in those cases, especially optical fiber damage from high radiation levels for MSRs. Where there's really no question there, but do you have any thoughts on that?
Yeah, again, I'll jump in. Sam, please add. That comment is spot on. Any sensor is going to be limited to providing information based on where you've put it in your process. Now, keep in mind, we do a wide range of applications, from where we're talking about something on, let's say, a salt loop, all the way out to something on a main line for waste processing of legacy wastes, right? So that's why we kind of interchangeably use terms like inline monitoring or online monitoring or variants thereof. Much of those have subcontext that indicates whether you're talking about a direct line measurement, a slipstream measurement, or if you're looking at a batch process, you're directly in that batch in some context, right? And so all of those applications, we're going to be seeing what we can see from the sensor location. And of course, if you're in a slipstream or you're not on a main line, you are right. You have to back calculate what's happening in that main system. All of that to say that any information you can get into a process is going to be extremely valuable, especially if direct sampling from that process is going to be extremely costly, extremely difficult because of the hazard region, or even, questionable whether or not that's going to be truly representative of what's happening in the entire loop or batch based on where you're sampling from. So fair point. And calculation of what's going on in the main batch is something that has to be considered in, again, any sensor application. You also brought up the challenge of radiation damage. So that was one of the challenges we highlighted early in our slides as something that we have to work around. That's something we're very familiar with. We've done experiments before, or demonstrations before, where we actually intentionally damaged some of our optical windows via radiation. And we demonstrated how we can use advanced modeling to overcome that challenge. Now, really, when you radiation darken any of your windows or your optics, what you start seeing is a decay in your signal intensity, as an example. There's some other effects as well. But what we can do is build in models that can handle that loss of signal intensity, because really what you're seeing is an increase in your signal to noise. And as long as you have your modeling built for that, you can start understanding, anticipating, and mitigating for that impact. And really what it comes down to then is understanding when you need to get in and replace those components, right? When you need to get in and otherwise maintain them. And really that's determined by operator needs when they're going to set that cutoff threshold for uncertainty or error in their measurement.
I'll add to that. So one of the applications that I mentioned at the very beginning of when I started talking was that the pre-treatment engineering platform that we supported, that even though we could measure online, it was more valuable for our customer at that moment to have a fully QC passport compliant procedure, which required matrix spikes added and lengths and etc. Things that are very difficult to do online. We could do those offline, and we had our Raman measurement that could take a sample in with essentially no pre-treatment of the sample except for a matrix spike added. We're able to measure that and get an analysis back within a 24-hour period, which was much faster than any commercial laboratory. You'd have to send it off to the laboratory and get a result back. So that supported them in a way, even though we could have done it online and had an immediate real time. The 24-hour return time was adequate for them, and that's something that is even considerable for even a molten salt reactor. We have something that could be, again, at line, that would be a graph sample that would be taken in with immediate response back from the laboratory.
Thank you. Another observation, uranium solids and chloride salts is really bad.
Yes. So I'll be honest, when we were running this experiment, we didn't anticipate that those solids would precipitate that way. That was actually a little bit of a surprising chemistry experience for us, and that's summarized really nicely in that journal article Sam highlighted there, first author Shamir Branch. But ultimately, in that particular system, we were trying to understand what happens in a process where you don't have that direct and immediate redox control via either electrochemical means or chemical means, because we were really trying to see what goes on in that salt, you know, if it's left to its own devices and you have potential interference or contaminants in there. So it was a really useful exploration of the things that we need to be cognizant of and mitigate for when we're doing our chemical control of these molten salts for molten salt reactors.
Thank you. Kind of sticking with that same, when ICL is monitored as gas, there would be a decomposition of the molecule. Is decomposition of ICL taken into consideration?
Oh yes, it was, in fact, and I didn't point it out. Sometimes I do. On the slides that I presented, you can actually see some hydrolysis products, HCl. There's some fine structure down at very low wave number region, around 100 wave numbers and below. You can see the fine lines from the HCl. And so, yes, we saw the hydrolysis product from ICL as I mentioned in the HCl. So yes, we can see the decomposition product there. And I'm not sure if the questioner was asking of other products, but other products, for example, if you have other halide mixtures, certainly those would be Raman active and or infrared active.
Thank you. Can you please expand on the internal reflection element and how it works?
The internal reflection probe?
Yes.
Yes, that's an attenuated total reflectance technique, and there's a lot of papers in the literature on the ATR element. In fact, we have a manuscript that is being submitted. In fact, it's under review, so it's going to be published in the we anticipate within the next several months. But it describes the attenuated total reflectance. So if you have a waveguide and you shine light through the waveguide, at the interface between the waveguide and the medium that's adjacent to that, if there's a difference in refractive index, and depending on the angle of incidence of reflection, you get an internally reflected light. At that interface where the reflected light is interacting between those two medium, you get an evanescent wave being produced. And the solution, depending on the chromophore in solution, it can interact with that evanescent wave, either absorb some of that light, or maybe it doesn't absorb, depending on the chromophore. And so you're measuring the light that is, it's like an absorbance technique. It is an absorbance technique because some of that electromagnetic radiation is being absorbed by your sample, and what you're measuring is a difference in energy of the resultant wave that gets to your detector. So of all the light that is reflected down the element, you're looking at a blank without an analyte present, and then you're looking at a sample with analyte present, and you're looking at a difference of the electromagnetic radiation that gets to your detector. And it's the ratio of those two beams that gives you that transmittance of light. Then you can go ahead and then do the calculation to form the absorbance. But if you're looking at what fraction of that light is being absorbed by your sample, and it's through the evanescent wave penetrating into the solution. And it's summarized better than I'm explaining it in journal articles. I can send, if somebody wants to send an email to me, I can go ahead and direct them to some literature on that.
Great, thank you. Excellent collection of very relevant data. Have you tried applying AI to learn from this data for classification and prediction?
So we'll say that the chemometric modeling that we do is a form of machine learning. You know, machine learning being an extremely broad term that also does, in some ways, include AI in there. Generally speaking, most of the modeling we approach in the chemical data science modeling realm is chemometric modeling. And we'll call that a little bit more old school in terms of how we approach data analysis. And there are reasons why we like that. You know, we are in the nuclear field where if we're looking at field or real life applications, we've got a huge regulatory burden on us. So there's going to be a lot of desire for, we'll say metadata, things that quantify our uncertainty. So Q residuals, student T squared residuals, all of that stuff that can tell us what our trust factor is for a given measurement, which is why we tend to utilize those older models, those older algorithms, because they really have a lot of metadata that can come with them and a lot of historical trust with the model results and performance. Now, we are secretly, not secretly, very excited about the potential to work in AI and how that can give us more flexibility and agility in some of these complex and harsh systems. But it's something we're moving into, we'll say, carefully, because again, we need to make sure that we're using algorithms that can give us that metadata, that can tell us our trust factor, and that themselves are very well proven and justified out there in the literature or in practice, so that folks can feel confident in the values that our systems are giving them.
Thank you. As optical properties of fluids, molten salts, for example, change with temperature, how do you account for the temperature during the calibration?
That's a really, oh, Sam?
Oh, I'll let you go ahead. I'll have a follow-up.
So temperature impacts are a really good question. Molten salts are a really good example of an area where you're going to have larger temperature gradients, but you do have temperature gradients in a lot of other processes as well. There are multiple impacts from temperature variations that can impact our speciation, it can impact our optical fingerprint, it can even impact, as you say, maybe some of our optics performance and all of that. So all of that is signal variation that we have to keep in mind. And when we build our chemometric models, essentially we have to build in robustness to that variability. So we have to, in our training sets, capture what we think those fingerprint changes, those sensing changes are going to be, so that when we have our quantification tools in place, they're ready to answer that. And Sam, I'm sure you have something to add.
Yeah, I'm glad you went first, because I'll just go very specific now. In the example of the ICL that I showed, sometimes I don't even show the slide, but I showed it today. where I showed the 4 principal components that were pulled out of the variable ICL data. And I mentioned that we can analyze this data with essentially 2 principal components. The first principal component looks almost identical to the spectrum of ICL at 1 temperature. The second principal component looks broader. And so it turns out the first principal component there is really talking about the variability in concentration. The second principal component is looking at the variability in temperature. So Amanda was exactly right. To go ahead and have a robust sensor that uses that can predict under variable conditions of temperature and the concentration range you're interested in, you need to have a training set that has both the variability in temperature and concentration for the conditions that you would expect that sensor to see. If you train it only on 1 temperature, then your system is actually operating on variable temperature, on a different temperature and variable temperature especially, then that's not going to be as robust as a model that was built using the variability of concentration and temperature that you have in your actual system. So you need to be prepared for that and just incorporate that into your model, so the model can then, through the multivariate type of analysis that we use, then can adjust for that.
Thank you. And I think as we've talked a little bit following your presentation, some of these thoughts may have already been addressed, but do you have any additional comments on what are some common strategies or technologies used to mitigate the challenges and limitations faced in optical spectroscopy, such as resolution limitations, signal noise ratio issues, and calibration errors?
So I'll jump in first and let Sam add in. And I'll say that this is a real life sensor and we're talking about extremely challenging applications. So there are going to be a lot of hurdles that we have to overcome to not only get a sensor into our chemical process, but then have it survive an extended period of time and continue to provide us reliable and trustworthy and accurate data, right? So you touched on some of those challenges, calibration being one, right? Ultimately, for all of our applications, we have to take a very in-depth assessment of what the challenges are for that particular application, what the lifetime is needed for that sensor, and what type of frequency we would actually be allowed for getting at, maintaining, adjusting, or so on our sensor process or our models. Ultimately, it's a little bespoke, again, to every application, and we take into account. But I'll use calibration as one example to kind of give you some insight into some of the thinking and processing that goes on with that. So typically when we, let's say we get a new instrument, what we do is we check, we verify our calibrations. What we like to do is verify that instrument against a set calibration set of really well-characterized standards. So we kind of get a fingerprint in time of what's going on with that instrument. You know, then we'll train our systems, we'll make sure our probes are behaving well, we'll get the probe out into a system. And then forever through the life of that, what we're doing is we're periodically checking how that system's performing against standards. Now, whether that's a standard you measure on your probe out in the hazard zone, that's questionable, you know, or if that's a standard you're measuring in a secondary standard cell closer to your instrument outside of a hazard zone that your operator can actually access. So there's different games you can play with checking your instrument performance and calibration via those means. There's also frequent check-ins or maintenance of our models. So, you know, you can't build a model in, 2020 and then make sure or feel very confident that it's still doing exactly the same thing in your process in 2024. What you have to do is check in periodically and say, oh man, are my pipes starting to corrode? Am I starting to see some iron in this that I need to now account for and update my model for? Has my instrument been hit a couple of times since it's out in the field? And sometimes people are clumsy and like to kick instruments. Did that impact our calibration of the instrument? Do we need to update the model and the maintenance for that? So there's a lot that you have to do. You have to take care of in these systems, just like any sensor you'd have out in the field. In terms of resolution, so that's kind of something that's set with each instrument. And again, it's something that we specialize for each application. What resolution is truly needed to give us the analytes that we're after? Hopefully that hits your question. I know that that's a very broad answer.
Sam, did you have anything that you were going to add to that? You just want to move to the next one or let me know?
Oh, I think we're ready for the next one, Britta.
Okay, great. This comes in from Ivan with CMAT in Spain. He's interested in knowing whether Raman's measurements of real solutions with high concentrations of radionuclides, for example, pure X raffinate, you anticipate high fluorescence from the solution that could affect the accuracy of Raman analysis due to overlapping signals. Excuse me, overlapping signals. Do you have experience on?
Yeah, that's a fun one. We've actually looked at both simulated raffinate streams from a PureX process, as well as, Sam, you looked at real raffinate streams.
Yes, we did. So this is where I mentioned when I talked about some of the deuterium hydrogen measurements, where we look at, I mentioned we purposefully look at various excitation wavelengths for our Raman technique. And the reason we do that is, you can get different sensitivities based on excitation wavelength. They can also dial in, if something is fluorescing, you want to go as red as possible so you're not illuminating up into that electronic transition that you start getting fluorescence out of. If you go more and more red, you tend to get less fluorescence. You tend to also get less and less sensitivity in some of your measurements. So it's a balancing act. You want to go blue enough to get more sensitivity, but you want to go red, more red, so you reduce that fluorescence. So we choose them judiciously to go ahead and minimize the effects of fluorescence, but also getting the high enough sensitivity that we need. And in fact, for the actual raffinate that we did measure, Raman was very useful in that, and we used the 671 nanometer excitation for that, and that was an article in Journal of Radionuclear Chemistry. And in fact, if the question asker wants to send me an email, I'd be happy to go ahead and supply him with a couple of references of where we measured some actual waste. Excuse me, some actual raffinate, fuel raffinate samples.
Thank you. Another observation, we need a way to monitor for loss of U or PU in MSRs.
So I think that molten salt example that Sam went through, it provided a really good example of looking at uranium in molten salts. And that one is a lot of fun because we were following uranium in multiple oxidation states, so we could see it in multiple oxidation states. But directly to your point, monitoring for loss, I mean, Sam directly showed in that example that we could see, we'll call it a quote unquote loss of uranium. Really what that was our uranium was not fully dissolved, right? We had some precipitants in there. So that's a really good example showing that we can see a lack of dissolved uranium in your system, otherwise indicating that some of your uranium is not where it's supposed to be. Maybe it's precipitated, who knows what. So optical spectroscopy is a powerful tool for that, for sure. Regarding plutonium, we're actually just starting to dive into some plutonium work now. One of our team members, Shamir Branch, is really leading that work, and that's under Ben Sapiti's Advanced Reactor Safeguards and Security campaign. And she's seeing some really exciting stuff, and hopefully we'll be able to pull out a manuscript of that relatively soon and get that out into the literature for folks to peruse.
Super, thank you. It looks like there is another, temperature can affect the results. What's the importance of temperature on those models? Do you have more thoughts on that?
Well, I think we already hit that a little bit, but yeah, temperature is very important. I think, you get band, I'll just say in general what I didn't say before, you get band broadening generally at higher temperatures. So if you're looking at Raman spectroscopy, for example, you're looking at a vibronic transition. And in vibrational transitions are affected by temperature. As the molecules heat up, the bonds are essentially lengthening due to temperature effects. So that affects that vibrational transition. And so you need to go ahead and build that variability, temperature variability into your modeling, just to capture that bond broadening or bond lengthening effect upon increasing temperature. And similarly, the electronic transitions, less so, but are also affected by, in UV vis, for example, electronic transitions are also affected by temperature, and so you need to go ahead and fill that in too.
Thank you. We've worked through most of the questions. There's one remaining observation. We need to replace the moderator. Hydroxide purification for MSRs, hydroxide being a moderator, bad for on fast reactor MSRE, almost had a recriticality due to having moderator on that purification system. Again, I'm not sure there's a question in there, but is there anything in there that strikes you as discussion points?
I'll just go ahead and just say that's outside of my area of expertise about moderation, moderators, and to even offer an opinion on that. Amanda?
No, I think that that's probably a great observation, but I think that a comment would be better from a reactor or nuclear engineer.
Thank you. And I think we've worked through all of the comments and questions through the list. We've just passed, well, we're into 100 minutes, so that is so fantastic. I think you can tell from the level of questions, the interest in your work and the appreciation for your expertise, and I echo that. So Patricia, if you have any last minute thoughts, I think we're ready to conclude and thank our presenters one more time.
Yes, Bertha. Yes, we were a bit late, but it was really worth it. I would like to thank you both, Amanda and Sam, for taking the time first to prepare the presentation and to present its excellent webinar. I'm really happy that we were able to capture your knowledge today, and this is being recorded, so people will be able to listen again to this webinar. So thank you again, Sam, and thank you again, Amanda. And as always, thank you very much, Bertha, for moderating this webinar.
You're very welcome.
You're very welcome, Patricia, and thank you, Berta, for moderating well and keeping us on track. Thank you very much.
Indeed. Yes, thank you.
You're very welcome. All right,
Goodbye.
that'll conclude where we're at today. Thank you. Bye-bye.
Bye-bye, everyone.
Bye-bye.
Thanks.